In this video, we're going to talk about domain of functions. The domain is probably one of the most important things we talk about with functions. We're going to talk about domain all through this semester. You will have domain questions on every test. So really try to understand the concept behind domain. Okay, so when we are talking about a function, and we defined it as taking the items in a set and making a relation with another set, right? The first set where we assign it a certain value in the second set, the first set, that's the domain. And it's important to know which one is the domain. Okay? Totally different. In fact, this relation here, if we use this first one as the domain and the second one is the range, it's a function, fine. But if we switched it and if we had this be the domain and we went the other way, it wouldn't be a function. So when we write, when we find domains, we write it as a set. Okay, so the domain of this is the set of numbers 1, 2, 3, and 4. Okay, so I'm doing it in set brackets because I can list them. The range here would be 4, 5, and 6. Domain and range are not always the same. They're not always the same size. They could be though, but they don't have to be. Okay, so let's think about this function right here. If you were going to graph this, you should recognize this as a line, right? A line with slope of 2 going through 1. When we have an equation and we're trying to find the domain, we're trying to think about what are the possible numbers that I could put in for x. In fact, really, most things you can put anything in for x, any real number. And we are talking about real numbers here because we're talking about graphs. Okay, so there's nothing that would stop us from putting any number in for x here. So the domain would be, we'd write this in interval notation from negative infinity to infinity. Okay, so it's all real numbers. And what about the range? To get the range, you really have to think about the graph. So we won't do range with everything. We'll do a few things that we know the range on, but everything we have to find out the domain because you have to know what you can plug in. In this case, it's a line, and we know the range is also all real numbers. Alright, this one is our basic x squared. It's a parabola, right? Starting at 0, 0 and going up. Is there anything that would stop us from plugging in an x? No, I can take any number and square it. So the domain would be all real numbers. The range, we have to think about the graph of this, right? So it looks like this. I never go negative, right? So my y values are only positive, and so it can be 0, and it goes up to infinity. That would be the range. Alright, let's look at some more now where we don't have all real numbers. We have to look at what are the possibilities for what I can plug in here. If if I tried to get, if I did f of 1, it would be 1 over 1, that would be 1. That's fine. If I did f of 2, it would be 1/2. If I did f of 1/2, 1 over 1/2, that would be 2. That's fine. But what if I do f of 0? Well, then I get 1 over 0, and that doesn't exist. Right? So if I plug in 0, I don't get an answer. It's not an answer at all. And so 0 cannot be plugged in. So the domain of this would be everything except for 0. The way we write that is we go from negative infinity up to 0, but we don't include 0. And we union that with start at 0, but don't include 0, up to positive infinity. Okay, so that would be my domain. I'm not going to worry about the range right now. We will talk about the range of some of this one in another video. Most of these we're not going to talk about range right now. Okay, so you probably noticed that the x in the denominator means, yeah, we have to worry about finding what the domain is. If there's no x in the denominator, like in the previous ones, we can plug in anything. The domain would be all real numbers. In fact, there are only 3 cases where the domain is not all real numbers. We're going to talk about 2 of them right now, and one of them a little bit later. So the first one is this, when we have a variable in the denominator. You have to make sure the denominator is not 0. Okay? So look at this one. We have an x in the top and the bottom. The x in the numerator, that doesn't matter. It can be anything. It's only the denominator that matters. Okay? I cannot let the denominator equal 0. So where would this denominator equal 0? Well, it's easy to see this without even doing the work, but in case there was one where it wasn't so easy to see, we just set the denominator equal to 0 and solve. Right? So if x is negative 4, the denominator will be 0, so that means my domain cannot be negative 4. So in interval notation, we would go from negative infinity to negative 4, don't include that negative 4, and then from negative 4 to infinity. Remember that I'm doing all real numbers. Okay, I can't say, oh, I'll just go up to negative 5, because what about negative 4.1, negative 4.7, right? All those have to be included. And we can get infinitely close to negative 4, but we just can't actually do negative 4. Now, you may occasionally see this written in set builder notation, and we would write the set of all x such that x is not equal to negative 4. So that's how you would write the same domain in set builder notation. So we see it both ways. The majority of the time we're going to do it in interval notation. There's one more like that. This one is a little bit more complicated, right? And this is still the same idea. We can't let the denominator equal 0. So I can just set the denominator equal to 0 and solve, right? So I think I can factor this one. If I couldn't factor it, I would plug it into the quadratic formula. Let 2 numbers multiply to be negative 15 and add up to be 2. So that'd be negative 3 and 5. Alright, so it equals 0 at negative 5 and 3. So now I have 2 numbers that are not in my domain. Now, I would write that as, in interval notation, it starts getting a little bit awkward. I go negative infinity to negative 5, union, negative 5 to 3, don't include those, union, 3 to infinity. A lot of people, when they write this down, they tend to forget this one right here. We can use this interval, we just can't actually use negative 5 and 3. So don't forget the middle one. When we start getting more little individual numbers that can't be used, then sometimes set builder notation is more convenient. All the x such that x is not equal to negative 5 or 3. That's also a possibility for writing domain. So we also have another case where we have to consider possibility for a domain, and that's when we use a square root. Because like I said, we're talking about real numbers. We want to be able to graph it. We're working in the real numbers. So even though if I plug in negative 7 here, and even though I can get an answer, right? So I would have square root of negative 6, which would be, square root of 6 times I can get an answer, but it's not a real number. I couldn't graph that because those are not on our normal graph. So I only want real numbers that I can graph, right? So that means what's under the radical has to be greater than or equal to 0. It can equal 0 though, right? There's nothing stopping it from equaling 0. It's not in a denominator. It's just under the radical. So I can just take what's under there and say, let's make this greater than or equal to 0 and solve. So x is greater than or equal to negative 1. So my domain would be everything from negative 1 to infinity. Now, here's one of the reasons that we did that earlier section. I have a quadratic under the radical. And you might even think about the fact that this 3 out here, this 3x, it totally doesn't matter. It has absolutely nothing to do with the domain. It just doesn't matter. So you can ignore it. We're only going to look at things that either are under a radical or have a denominator. So I just take what's under the radical, set it greater than or equal to 0. I can factor this. Difference of squares, right? I look at the number line. I have negative 2 and 2. A number less than negative 2, like negative 3, would give me a negative times a negative, so that would be a positive. A number in here like 0 would give me a positive and a negative, so that would be a negative. A number bigger than 2 would give me a positive and a positive, so that would be a positive. So my domain is negative infinity to negative 2, and I can include it, right? I can include it because it's okay to be equal to 0. Union to infinity. Let's quickly just look at one more. Here we have h of x that's a cubed root. So a cubed root, remember, it can be negative. It can be negative or positive or 0. It doesn't matter. There's no restriction, right? It's only the even-powered roots, the even-indexed roots that matter. If it's a cubed root, it's always just going to be negative infinity to infinity, unless there were a denominator inside of it or something. Then we would have to worry about that. All right, here's your quiz question for 3.1. That should be a 3.1b. Sorry about that. 3.1b. So there's your question for the quiz. Write it down and give me the domain for that.